Okay, so let us now discuss one by one the dimensionless number that I have mentioned last time. So let's start with the Nusselt number. Nusselt number NU, right? The symbol is NU. Okay, so so this Nusselt number here NU represents the actually it represents the enhancement of the heat transfer through a fluid layer as a result of convection relative to conduction across the same fluid layer. Okay, so simply if we can see uh, the fluid, right? Say this is our uh, fluid, right? Say this is our fluid. Okay, okay. So this Nusselt number here, actually, it only represents the enhancement of heat transfer through this fluid layer, through this layer. Okay, 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 okay. So it I mean it only shows the um, the enhancement of heat transfer as a result of uh, convection relative to the conduction, right? This is this fluid layer is in contact with each other, and the Nusselt number actually only represents, yeah, that enhancement of the heat transfer through this layer as a result of the convection relative to the conduction across the same fluid layer. Okay. So since the Nusselt number only shows the relationship of the heat transfer as a result of convection relative to conduction across this layer, then we can see that the larger the Nusselt number, the more effective the convection is. Okay, so the larger, the more effective the conduction. So if we have now a Nusselt number equal to 1, since this is only a convection relative to conduction, and if this is equal to 1, it only means that uh, this fluid layer represents heat transfer um, across the layer by pure conduction, right? Okay. So last time we also say the expression of the Nusselt number, which is equal to H LC all over K. Okay, once again, our H is our heat transfer coefficient, our L is our characteristic length of the geometry in meters, and K is our thermal conductivity. Okay, we already know we are very familiar with the heat transfer coefficient as well as the thermal conductivity of our material. Then let me emphasize to you now the what we call the characteristic length of the geometry in meter. Okay, say this characteristic length um, differs by which it depends upon your um, your uh, your geometry. Okay, that's why it is called the characteristic length of the geometry. So we are talking about the length here. So if we have, say, this this is our surface, then our fluid, say air, is moving around this direction, having this covering this surface, then our characteristic length here is this part from here up to here. This is now our characteristic length. Okay, so the measurements of these characteristic lengths depends upon the the um, the the contact between your fluid and your surface. Okay, so the characteristic length, say for example, you have um, a pipe here. Okay, so we have a pipe, then we have a fluid going on this uh, pipe surface. Okay, so the characteristic length here is this part, this part. Okay, okay. Again, if you view this, the plate and the airflow, the characteristic length is this. But if we have different geometry, the characteristic length of the geometry of this pipe here is this one. Okay, when if the flow is this part, if the fluid flow is this one, okay, it will go here. So the length is this one. Okay, so we will be having some examples later on, so we can appreciate it more. But before we proceed to some applications and some sample problems, then let me first um, discuss the other dimensionless number. Okay, so let's now move on to the Prandtl number. Okay, by the way, once again, the Nusselt number, ano nga, it only represents the enhancement of heat transfer through the fluid layer as a result of your convection relative to the conduction, right? Okay, so now let's move on to the Prandtl number. Prandtl number is another dimensionless quantity wherein it puts the viscosity of the fluid in relation to the thermal conductivity. Okay. So the Prandtl number only shows this correlation, okay, the viscosity of the fluid and the thermal conductivity. Okay. Therefore, if we assess this relation, this two relation, we can now see that this is about the momentum transport. Okay. It is about the kinematic viscosity of the fluid. And this one here naman, the thermal conductivity, we can assess this as the thermal transport, thermal transport capacity of a fluid. Thermal capacity of a fluid. Okay. Okay, once again, the Prandtl number only relates the viscosity of the fluid and the thermal conductivity. Okay. In another perspective, we can view this, the thermal conductivity, as the relationship between the momentum transport and this thermal conductivity as the thermal transport. Okay. Therefore, last time we say that PR is equal to this one, mu Cp all over K, right? So mu Cp all over K. Okay. So actually this is the derived formula, but if we take a look at this relationship, the viscosity and the thermal conductivity, or in terms of the momentum transport and the thermal transport, or the capacity of the fluid, the thermal transport capacity of the fluid, we can define this Prandtl number as the kinematic viscosity. The kinematic viscosity, this is about the viscosity of the fluid, and of course the thermal diffusivity, right? Okay, and if we're gonna derive this, the thermal viscosity of a fluid um, is actually equal to the dynamic viscosity all over the density, okay, of the fluid. So we have the uh, dynamic viscosity all over the density of the fluid. Okay, so that is the kinematic viscosity of the fluid. Okay, but if we take a look at the thermal diffusivity, the thermal diffusivity now is actually K, the thermal conductivity, all over rho Cp, right? So that is A, or the thermal diffusivity. Okay, and if we gonna do some mathematics here, we can cancel this out, and we can now come up with the mu Cp all over K, right? So this now now is our derived um, formula for the Prandtl number. Okay, wherein our mu once again is the dynamic viscosity. Okay, our Cp is our what? Yeah, our specific heat, or Cp. It can be in terms of joules per kilogram K. And then our K is of course our thermal conductivity. Yan. Okay. So we can now have this Prandtl number, okay, as our equation. Okay. As you can see, once again, we can now recall that the what they call this, the heat transfer coefficient, the factors and the properties related to that coefficient, again, is that it includes this, the viscosity, the thermal conductivity, and so on. And the Prandtl number is responsible, is a quantity that puts the viscosity of the fluid in correlation with the thermal conductivity. Okay,